early hour or at all. So I hope microphone is on and everything. Yeah, okay. Yes, so we're going to explore today some more of the consequences that subordination has on the study of free convolution. And so one of them is the fact that it eases to some extent the calculation of free convolutions. In a few cases when you can do it a little faster with the subordination functions. So I'm going to start with this. I mean, this is my sample example. It's the only one that I'm going to calculate. It's the case of two Bernoulli variables. So mu1 and mu2 are freely independent and distributed according to this distribution. Probability of 1 and -1 are equal to 1/2. It's what so one might call two free coins. I mean, who doesn't like free coins? Let's see. We should be able to say something about that. So mu is the free convolution of these two measures. So f mu is equal to f mu1 of omega of z. There's only one function, omega of z. Omega 1 and omega 2 are the same because the two measures are the same. So the right-hand side of that equation that says that f of the convolution is omega 1 plus omega 2 minus z tells you that this is 2 omega z minus z. Okay, so let's calculate a little bit. G mu 1 of z is the Cauchy integral of this particular distribution, 1/2 1 over z minus 1 over plus 1 over z plus 1, which you add up, and you get z over z squared minus 1. And the reciprocal Cauchy transform is z minus 1 over z. Therefore, the equation that you have for omega is omega of z minus 1 over omega of z is equal to 2 omega of z minus z. Well, that's an easy equation to solve. It's a quadratic equation. And I did the work already. So that's so here it is. It's omega of z is 1/2 z plus square root of z squared minus 4. The same discussion about the square root, right? You have to be a little bit careful how you define the square root. Therefore, g mu of z, it's g mu 1 of omega 1 of z, which is omega over omega squared minus 1, which is, after a little bit of an algebraic calculation, 1 over the square root of z squared minus 4. So you notice how this is real and analytic outside the interval from -2 to 2. And let me see if I made that mistake again this time. No, this time I got it right. So the measure mu is 1 over pi times the square root of t squared minus 4 minus t squared. Sorry about that. I did make the same mistake. 4 minus t squared, or if you can put an I in front of it, but that's what it is. 1 over pi square root of 4 minus t squared dt on the interval from -2 to 2, which is the arc sine law. So it's a kind of a different situation from and I wanted to also contrast this with the computation of atoms. So if you take two non-free coins, two independent coins, you have two non-independent coins, and you convolve the corresponding measures, what you get is a discrete measure concentrated at -2, 2, and 0. Here, all the sums of two atoms appears -1 plus -1, 1 plus 1, and 1 plus -1 all appear as atoms. And this one doesn't quite seem to be the same way. I mean, it's the effect, you'd expect the effect at 0 to be the strongest of the addition of these two variables, but it's the weakest, in fact. Right? So, yes.
So if you modify those measures, you change the ways that an atom appears, the calculation still is
as easy as this. Yes. So if you, of course, it's a little more complicated when you take two different measures. So that's a fact. But still, it reduces generally to solving one quadratic equation rather than 3. That's a small advantage. But of course, we all know that, this kind of calculations grow out of hand very quickly. It's as soon as you have measures with 3 atoms, you no longer can calculate these things, even though they are usually algebraic functions, and everything should be very nice. Three-sided coins are, even if they are not so easy to deal with. Okay. Okay. I want to get back to the Julia-Kara-Theodori derivative. A little bit, because there's a little bit of a there's the property of this Julia-Kara-Theodori derivative, which is yeah, well, 2 properties. So this is one of them. So suppose that F mu, that the reciprocal Cauchy transform of a measure mu fixes 0. Notice fixes is with quotation marks, right? So that means that f of iy tends to 0 as y tends to 0. So f of, in this case, I can calculate there's a Julia-Kara-Theodori derivative of this function at 0, and it's given by this formula f prime mu at 0 is 1 over mu of 0. It's the equality. Well, how do you do that? So this is true even when mu assigns no mass to the point 0. The Julia-Kara-Theodori derivative in that case is just infinite. How do you prove that? Okay, well, it's since we defined the Julia-Kara-Theodori derivative using points at infinity, let's just transform the problem by moving 0 to infinity. So in other words, instead of looking at the function, so there's a conformal map that takes 0 to infinity, which is z takes to -1 over z. You have to apply it both to z and to the function. You conjugate with that transformation. So you look at -1 over f mu of -1 over z, which is minus g mu of -1 over z, which is an integral. The little change in the integral, it's in the integral of z over zt plus 1 d mu of t. And you see immediately that this is, you can isolate the mass at 0, mu of 0 times z, plus an integral over the realigned -0. That's going to be little o of z as z goes to infinity. So if you remember in the Julia-Kara-Theodori derivative, the first term at infinity is beta z, where beta is 1 over the derivative. So that's so that's what I'm thinking there. The Nevanlina coefficient at 0 is mu of 0, and therefore the derivative is 1 over mu of 0. Okay. And there's a second property of the Julia-Kara-Theodori derivative, which is something that we use all the time in calculus, is the chain rule. Is there a chain rule for the Julia-Kara-Theodori derivative? Turns out there is a chain rule. I don't think ever anybody writes it down, but it's possible. It's possible to write a chain rule for the Julia-Kara-Theodori derivative. So suppose that I have a function f, which is 2 functions, f1 and f2 from the upper half plane to itself, that both is 0, and so does the composition f1 proposed to f2. That's not an automatic statement, yeah, that the composition has to fix 0 as well. So I'll just assume that all of them fix 0. Then there's the chain rule that f prime of 0 is greater than or equal to f1 prime of 0 times f2 prime of 0. So it's exactly the chain rule, except it's greater than or equal to 1 before. When the numbers on the right are finite, there are cases in which it is equal. So let me not discuss this, we'll come to the equality case in a moment. So I have this chain rule for how do we prove it? Well, let's look at so if you remember, the Julia-Kara-Theodori derivative was written as limit inferior as z goes to 0 to the imaginary part of f over the imaginary part of z, right? So let's look at that. So imaginary part of f of z. I don't know where it is. I never see it. Well, okay. This is not for me. This particular tool is not mine. So you just write it as imaginary part of F2 of W over the imaginary part of W times the imaginary part of F1 of Z over the imaginary part of Z, where W is F1 of Z. Yeah. So and I know that F1 fix is 0. Therefore, there are some sequences of points with the property that, let's say, Zn such that Wn converges to 0, right? It's like, well, so anyway, so what you want is the limit inferior of the left-hand side, and of course, on the right-hand side, you don't get arbitrary combinations of Z's and W's. You just get some of them, and that's why you get an inequality rather than. It's like the same as with the infimum, supremum, if you want. Supremum is some multiplicative, right? It's not exactly multiplicative. So let me just spend a little bit of a moment to explain when it happens that that you have equality. Well, it might be yes. So there was another characterization of the Julia-Cartier derivative, which said that the derivative is the actual angular limit of the distance from f of z to 1 over the distance from z to 1. Z approaches 0 non-tangentially. So for instance, in here, if I knew that if z approaches tangentially, the point 0 f w also approaches non-tangentially, then I do get an exact equality in that case. Yeah, because you have limit rather than limit inferior. So that happens. That happens, for instance, when the Julia-Cartier of f1 says is finite. That's something that happens in that case. Okay. Oh, find flaws and fix them. It's a red herring. But if you find some, let me know. Okay. So now a few words about absolute continuity. I mentioned this this a little earlier, the absolute continuity. So let's take two non-degenerate measures, and we already know that the reciprocal Cauchy transform of the free convolution can be written as omega1 of z plus omega2 of z minus z with the corresponding subordination functions. And we also know that omega1 and omega2 extend continuously all the way to the real line, possibly with infinite values here and there. But this tells you that the Cauchy transform and the reciprocal Cauchy transform of the free convolution is a continuous function on the entire upper half plane, which doesn't happen for every measure, right? So there are measures for which this kind of thing does not happen. The measure can be very irregular, but this already tells you that there's something pretty reasonable. It doesn't tell you that the measure is absolutely continuous. It is possible to have a continuous Cauchy transform for rather singular measures, but they have to be kind of special. They have to be concentrated on sets of small capacity. But there's a lot of literature on that particular subject. It's probably not familiar with this particular circle of in our circle of ideas, but the people who have studied function algebras would know about these things. Okay, theorem. This is Sherban-Belinsky's result, that the measure mu is in fact absolutely continuous except for those finitely many atoms that might arise. And so I'm very pleased to present to you a complete proof of this. So you see, I said that I was going to have 0 proofs today, but that was a lie. So I'm very happy that I can present the presentable proof, because this came out in a series of several papers that that used a lot more mathematics than we do here. Okay, so let's look at the Poisson integral of the measure mu. The Poisson integral of the measure mu is -1 over pi times the imaginary part of the Cauchy transform, and then it is a fact known the big, I think, perhaps in a slightly different form, that the limit of this function at is in fact infinite almost everywhere relative to the singular part. Yeah, so you have Lebesgue's theorem that tells you that if you have an increasing function on the real line, it's differentiable almost everywhere. But on the other hand, relative to the singular part of the measure, it's infinite almost everywhere. So there's this amusing behavior of a function which is both finite and infinite almost everywhere, depending on what we mean by almost everywhere. Yes. So we conclude that the reciprocal Cauchy transform f mu1, the reciprocal Cauchy transform of this free convolution is in fact equal to 0 almost everywhere. The singular support of the measure. All right, but now we just have we had the theorem a little while ago which said something about the Julia-Carathéodory derivative of the function at a fixed point, right? So let's just for simplicity, let's say that I'm looking at let's say that 0 is a singular point, so that we don't muddy the waters. Okay, so we'll say f mu1. So let's say that this convolution, this reciprocal Cauchy transform is equal to 0 at 0. And let's also say that omega j of 0 is equal to 0. Omega j of 0 has some value, but let's not worry about what it is. Omega j of 0 is equal to 0. And let's remember that the function phi, you remember phi sub z? Probably don't. But the value of omega 1 of z was the fixed point, or the tangible point of a certain function, z, which would be denoted by phi sub z. And when z is equal to 0, this is what that function looks like. It's h2 of h1 of w, except that this h is for previously that's the only change that we have. So I have to go back and edit that file for you to post. So mistake number 2. 0 is therefore the Dangeau-Wolff point of this map phi sub 0. And therefore, phi 0 of w, so phi 0 of w is h2 of h1 of w. And this is, I'm just repeating. So h1 of 0 and h2 of 0 are equal to 0. So now we apply the chain rule. The chain rule says phi 0 prime of 0 is greater than h2 prime of 0 times h1 prime of 0. Yeah. But what are, so in other words, it's h2 prime of 0, I say, is f mu2 prime of 0 minus 1. Just look at the formula for h. H is f minus w, right? You differentiate that, you have to subtract 1. And at the same time, the Dangeau-Wolff derivative of f itself at 0 is 1 over mu2 of 0, 1 over the mass of mu2 at 0. Same for the other one. So I get that phi 0 prime is greater than or equal to that. On the other hand, I know that phi 0 prime must be less than or equal to 1 because I'm at the Dangeau-Wolff point. So what do I get out of this? I get that that product there is less than or equal to 1. And now you chase denominator, multiply things out. And that reduces to the inequality that mu1 of 0 plus mu2 of 0 is greater than or equal to 1. That's what that is. Okay. In the more general case, when I don't have 0 as my point, f mu1, let's say f mu1 convolve with mu2 at the point t is equal to braces. All right. That's a function of t, right? Value at t is equal to 0. Well, omega 1 of t and omega 2 have some values. And mu1 of omega 1 of, we conclude that mu1 at omega 1 of t plus mu2 of omega 2 of t is greater than or equal to 1. So basically, you can translate everything to 0 by just translating the measures mu1 and mu2. So that's not a difficulty. Okay, and this kind of inequality happens just like the previous case of atoms. This only happens finitely many times. And therefore, the support of the singular part of mu must be finite, which makes it a discrete measure. Maybe I should say a few words about this, because just to explain how primitive is our understanding of distributions, operator value distributions, which are important in considering convolutions of other operations, so now, of course, we are very happy that linearization allows us to take any operation in free random variables and write it as a sum, one of a sum. But that so far has yielded not that much, not really satisfactory results. So I would say that. So here, for instance, we have the older result about atoms, that the atoms occur exactly where this sum of masses is strictly bigger than 1, right? Strictly bigger than 1. And you would like something like this to happen for several things. So let's say you want, you have several freely independent random variables and take a polynomial in them, and then you look at possible point masses of the distribution of that thing. The best result to date is the one in a paper by Octavio Arismendi and company, Speicher and Sebron, I think, Guillaume Sebron. So they have a very nice result that says that in some sense a polynomial like that has point mass. So the distribution of it has a point mass. Precisely when you apply the same polynomial to generic matrices of arbitrary values, you get a non-trivial kernel. That's the result, and it's not easy. So far, I think as far as operator value distributions are concerned, that's probably the best result that we have so far. This refers to atoms. That's very primitive compared to this thing, this result of Belinsky, which tells you absolute continuity. I mean, what does absolute continuity even mean in that? I mean, it does mean something. If you have several, if you take a self-adjoint polynomial of several self-adjoint freely independent random variables, that has a definite distribution. And I don't know, there's nothing so far that tells me that anything like that can have more singularity than point masses. But proof of that, I think it's over the horizon at the moment. Okay. Yes. And I wanted to make this note that the fact that so if you have 2 points alpha 1 and alpha 2 point masses for mu1 and mu2, where the masses add to something strictly bigger than 1, you get an atom. You would expect that when the sum is exactly equal to 1, you get perhaps not an atom, but maybe a singularity or something. It should show some decency. Let's say there's a big pain in the neck there. Right? But as we saw in the case of the Bernoulli, that doesn't happen. So if you take the 2 free coins, you don't get any mass at 0. So for the independent case, you get the most mass at 0. In the free case, you get the least density at 0. So, so that's not. So even this situation, what exactly is the singular support? Where does the function f blow up? is not entirely elucidated, but I think that's pretty close. I think we should be able to answer fairly soon. Okay. Yeah, let me, so I could mention several other applications of the frame. I'm going to be early again. Let me speak more slowly. Yes. So there's another fairly recent development related with subordination functions, which is the count of connected components. So this is something that has been observed some time ago. I think the first result of the time was due to Bian, who looked at the regularization of the measure using convolution with a semicircular. So so the Gaussian regularization, free Gaussian regularization of a measure. And what he discovered using analysis that could also be simplified with what we discussed here today. Yeah, what he observed is that the number of components of such a regularization decreases with time. So you look at the measure mu, you compose the semicircular of variance t, and as t increases, there are fewer and fewer components of the measure, and you kind of see them, growing, and kind of coalescing together. And where they coalesce, there's a special singular behavior at the point of coalescence. So instead of having a square root behavior, you get a cubic rooted behavior at those points. And this was subsequently extended to other processes of this type. So, for instance, if you take a measure and you take the powers, the convolution powers of the measure, either the integral or real coefficient, but perhaps the analysis is done a little more easily when the powers are real. Then again, the same phenomenon arises. In other words, the number of components of that power decreases with time until the at least for finite for boundedly supported measures, eventually all the components coalesce. Well, this was known before, but superconvergence will get you this solved. But this is true even for measures with arbitrary support. That's a result. I believe it's Howey, right? But do you have something to do with that also? Multiplicative, yes. So there are also multiplicative versions of these things. So Howey Huang proved this result about the decreasing number of components, and so this sentiment, if you want, that free convolution tends to decrease the number of components, and so there's a result related with this. So let's say that you have measures mu1 and mu2, and each one is supported by a finite number of compact intervals. So n1 intervals for mu1, n2 intervals for mu2, and mu j has a nice density on each one of those intervals. I'm not going to define nice density because it was all defined earlier in this meeting. It was what was called Jacobi measures for some reason. Yeah, so you have a nice density, positive, strictly positive on the entire interval, and at the endpoints, it behaves not worse than power. It's like a power, but between -1 and 1. The endpoint behavior. So they can blow up, but not worse than power 1. And let's say in this case, the convolution of mu1 and mu2 is going to be contained in n intervals, and the question is, what is n? And a pretty careful analysis was done by Bao, Erdős, and Cinelli. First, for the case when the support is connected, n1 is equal to n2 is equal to 1. And they concluded in that case that n must also be equal to two measures supported each one in an interval with the Jacobi density in that interval. I guess the Jacobi hypothesis comes from is interesting to them because of random matrix considerations. That's something that occurs fairly frequently, I guess, in that study, or is a useful hypothesis. And yes, and in the more general case, Morillon and Schnelli have proved that n is strictly less than 2 times n1 and 2. They have more precise estimates than this, depending on various parameters that they come. But one must admit that it's a little bit disappointing, this inequality, because I mean, come on, let's be serious. Regular convolution gives you n1 and 2 components at most. So this is less than 2 times n1 and 2. That's not quite satisfactory, but still it's a result. Yeah. So yeah, so they have a more precise analysis as to what happens with subordination functions in this particular case. And there's one way that these results can be improved almost immediately, which is that instead of saying that mu j consists of nj compact intervals, you can just say that the support of mu j has nj connected components. You don't really need to make any assumptions about the way the distributions work. And the reason for that is that every measure that's supported on whose support has nj components can be approximated arbitrarily well with the distributions which satisfy the hypothesis of this. So if you have any atoms and you have a single point which is in the support and it's isolated from the rest, you can just smear that over a small interval and moreover, this approximation can be made even at the level of random variables. So if mu1 and mu2 are the distributions of 2 variables x1 and x2, then you can approximate them with mu1 prime and mu2 prime, and mu1 prime and mu2 prime will be distributions of variables x1 prime and x2 prime, which themselves are very close to x1 and x2 in norm. This kind of smearing out and regularization of the densities is not going to change the norms of the operators involved very much. And so in other words, any situation with n1 and 2 components instead of compact intervals can be approximated with one that satisfies the hypothesis of Morillon and Schnelli, and therefore the convolution of mu1 prime and mu2 prime will satisfy this particular inequality. Yes. And now the distribution of mu1 convolved with mu2 cannot really have any fewer components. So there's an old result which whose name I was going to look it up, and it's a name that I always forget. But people in spectral theory know this result very well. If you have an operator that has I don't know 20 components in its spectrum, and you have a very close operator, then that very close operator will have at least 20 components in its spectrum as well, because you know that the spectrum has to be close to the spectrum of the limit, but each component of the limit has to contain something in its neighborhood. So I'm sorry? No, it turns out it's not Kato. It's somebody who wrote a thesis at UCLA in the 40s or so, and the result is not cited very much because nobody knows about it. If you want to read about it, there is a little book of yes.
Go ahead. I can finish your idea.
Yeah. So there's a little book by Bercovici, who puts great price on this particular prizes this result very much, and has a lot of developments around it. Yes.
So you expect the worst case for most compact intervals in the convolution to be when the original ones that point mass have the point mass. Is there any evidence that things that is the worst case?
No. Because you see that it's a so in principle you can do the things the other way around. You can say that every measure whatsoever you can approximate it with discrete measures, but when you approximate it with discrete measure, you have to put a lot of atoms in it. So that's the same argument is not going to go in that case. Yeah. But I very highly suspect that that is the worst case. That's really the case of point masses. So in essence, it's a statement about a real algebraic function. Don't know how to. Yeah. So for that particular case, probably the result could be obtained. I mean, maybe not strictly less than 2n1 and 2, but at most n1 and 2, you probably can obtain from Bezout. I highly suspect that Bezout is going to give you that much. So because you have an algebraic functions, and the question is, you have some zeros of an algebraic function of degree, probably about n1 and 2. So,
but my guess would be the max n1, the actual upper bound. And is there any example?
Well, if you look instead of looking at convolutions, you look at convolution powers, then it is violated for small values. So if you take the free coin, the free fair coin, and you look at the Nika-Speicher semigroup, that it generates for small values. For small values, you'll get two atoms, the two atoms that you expected to be, but there'll also be a little bubble around 0. So there are 3 components in that case. So I mean, they don't bring any evidence of a large number of components. So that's something that. I think that's an interesting issue, and I think one should be able to settle it one way or another. And I think it should be easier by using these little observations that we have here about the subordination functions. But it's a little tricky. Okay. So multiplicative, yes. So this is so the operator valued case I have discussed a little bit. But let me discuss it a little more, since so a little prior to the Arismendi-Speicher-Sebron Speicher result. Shaban and I and Wei Hua looked at this a little bit, again using properties of subordination functions, but in the operator valued context, to look at atoms of a polynomial into random variables, and our result is of a slightly different nature, though it can be deduced from theirs. But let me tell you what it is. So if you have a polynomial, let's say a self-adjoint polynomial, in several, I think we had just 2 in our case, but you can have several if you like. A self-adjoint polynomial in 2 free random variables. And such a polynomial has a point mass, let's say somewhere. The distribution of it has a point mass somewhere. Then we can get a little something out of it, and we can get that one of the variables also must have a point mass somewhere. So so point masses. So in the additive case, we just have two random variables. You can say a lot more, right? So the point masses of the sum are exactly sums of point masses for the first plus one for the first and one for the second, with the property that the point masses add up to more than one. So in the higher for higher degree polynomials, this is what we can say for sure, that there will be one of them. Yeah. And there are some difficulties with estimating what it is. I mean, we have a rough kind of estimate, but it's not really very sharp. So this is yes. So this is about operated value, and then that's, I think, is pretty. I mean, slowly but developing, I think, very nicely that area of. I mean, as you know, as we learn more and more about these so-called non-commutative functions, I think the analysis of this kind of process is going to be more understandable. Yes, everything that I've talked about in these lectures has been about addition of random variables. And of course, arbitrary operations on random variables can be dealt with using linearization. But there are two special cases. I mean, one special case is one particular operation, which is the multiplication of random variables, for which there is a direct calculation. You know, there's the Bercovici S transform. And there are also subordination results concerning that, and a lot of that, a lot of the theory that we do here can be reproduced in those cases. It is very unfortunate that you cannot deduce one from the other. So sometimes you have to do it over again. It's so it's not the upper half plane, perhaps it's the disk or something else, but there's no direct connection between these two operations. So there's a connection at the level of function theory. The function theory looks the same, though a little bit different, just a little bit different. So and there are three distinct domains that seem to be important in these three things. So for the additive convolution is the upper half plane that you have to look at. For multiplicative convolution on the circle, in other words, for multiplication of unitary random variables, you have to look at functions defined in the disk, which fix the origin. Yeah, so it's also a version of the Cauchy transform that does that. And for the multiplicative convolution on the positive line, one has to do function theory on a strip. It's strip. In which again you have a kind of a fixed point. You see, so in the case of the addition, you have the f that kind of fixes at the point at infinity. In the case of the multiplication of unitary operators, you have functions that fix the origin, and in the multiplicative case on the line, you have things that are defined on a strip in the complex plane that fix the middle line of the strip. I mean, not fix the point twice, but leave it invariant. So it's not an invariant point, but an invariant line in that case. So, but curiously enough, the theory can be worked out in all of those cases, and every single result that I have spoken about here is, in fact, true. Each one of those in each one of those contexts, and I think at this point. What's going on? Yeah. Thank you all for listening to me, and thank you especially to the organizers for inviting me to give these lectures.
For these results on three convolutions with semicircles, like an increase in semicircles, I think are their results, like you can see from the original measure how fast the support is.
I don't think that has been done actually to see how fast it goes. Yeah. I think one can probably, it probably depends a good deal on the measure that is involved, but probably once you know the measure, one can determine more or less when that happens, because everything amounts to basically the behavior of a single analytic function in the upper half plane on various domains. Yeah, so when you convolve with nothing, you just have the reciprocal Cauchy transform of the original function. And then if you restrict this to smaller and smaller domains, you just grow some bubbles around the real line and restrict to that set. So those are the images of the subordination functions in that particular case. And those are essentially level curves of some sort. So if you understand the measure very well, presumably you could determine more or less what these level curves are and see when they hit the real line.
Yeah. So instead of looking at sums of three subjoints, you look at some three varied measures.
We wish we could, but you know what? A lot of what yeah, there's been a lot of work on that, but it's a lot harder. It's a lot harder. So sums of well, sums of free unitaries, of course, those are going to be R diagonal operators, and those things are perhaps reasonable. Perhaps one can understand them. So after all, Hagerup and collaborators have determined the Brown measures of all the R diagonal operators and some using subordination, even though they don't say so. So if you look at the Hagerup-Schulz paper where they do this kind of thing, there is hidden in their subordination function. But yeah, but and in principle, also adding several unitaries, you know, amounts to an operation, perhaps with coefficients, constant coefficients, amounts to a certain operation on measures that Mika and I have been looking for a long time. There's a and King also, because there's a paper that had a long history. I think there's a little manuscript where we discussed how does one calculate the convolution of the addition of two and there are two ways of calculating. So one of them was the one discovered by Hagerup and Larsen, I believe, which amounts to basically free convolution of a certain symmetric measures, symmetric relative to the zero on the real line. So you can reduce that to free convolution to some extent, but then you have to apply this procedure that they discover for constructing out of that the Brown measure. So it's a little implicit, but I think all of that can be calculated. Yeah, so actually, you know, I gave you a tentative answer, but the answer to that, the truthful answer is that yes, it can be done. Yeah, what cannot be done so easily, if you add a, let's say, operator or something, that's trickier. Yeah. But I have to ask Ping about that. Yeah, no, not quite. Not yet. You'll have to ask Ping in a couple of months.
No questions. Well, let's thank Harris for the wonderful lectures here.